So good morning, everyone. Yeah, it is a pleasure to introduce you to, well, I'm sure that most of you already know him. So Paul Beck, he's been around for a while. He's now a Ramón y Cajal Fellow here at the Institute, although he was a Juan de la Cierva Fellow like 4 years ago. In the meantime, you've been a professor in GATS, although you've been regularly visiting the ISE, you know, these years, right? So yeah, so today he's going to be talking about sounding the treasure trove, Asteroseismology of red Gaia on the stars and binary systems. All yours.
Okay, thank you. That's, well, as already was mentioned, this I've been around a bit at the ISC since 2017. I'm either here a postdoc or a common visitor, but this is the first seminar, official seminar that I'm giving, so I feel honored. And the topic is on my specialty, on asteroseismology of red giant stars in binary systems. And so I want to separate the talk in two parts. First, just to highlight the tools we are having for asteroseismology. The main problem is, if we study stars, everything in astrophysics basically is built on one-dimensional stellar models. How do we know they work? You know, a three-dimensional model is wrong in 3 dimensions. So how do we get our model right? The problem is that all we get from a star is from a very thin layer. Here I provide you an Austrian model of a star, and this is pretty accurate because the photosphere, the layer where we get all the information, is about as thin as the aluminum foil for the whole body. If this would be 1.5 million kilometers, the aluminum foil would be about as thick as the photosphere. So all the information we get comes from this tiny little layer. And the art of astrophysics, of stellar astrophysics, is to reconstruct the whole structure below and beneath to calibrate our models. We can do that via simply trying to iterate the differential equations of stellar structure until they fit the surface. That's one way. The other way is that we actually try to measure the structure, which is hidden below the luminous atmosphere. The only way to do that is asteroseismology, by not looking, but listening beneath the layer of the atmosphere. And how does asteroseismology work? I give you another simplified model of a star, and we all know that if we knock on a barrel, what we get is a sound. And by the sound, we can tell if the barrel is full or empty, simply if we get a high-pitched or low-pitched tone. Because what is happening is that the whole structure is resonating according to the average parameters of it. And if the barrel is filled with a liquid, the average density, of course, is much higher than when it's empty. And we can apply that to stars. Of course, it's not recommended to fly to a star and knock. Well, you would burn your fingers. Luckily, stars are doing that by themselves. If we're looking at a sun like the star, we have convection. We know this is a high resolution image of the sun, and you see those granules. For reference, you have the size of the United States there, so they're about half the size. And this is convection that near the surface is reaching nearly the speed of sound in the upward movement. And when the heat is dissipated, the material flows down. And this shear between up and down flow, that is producing a noise like when you have a chalk on a whiteboard or a blackboard, you know, this itching noise. That's about what happens between the up and down flow layer. And that's a big, big subwoofer that is sounding the outer layers of the sun. What then happens, and I show this movie, well, I think every asteroseismologist is showing this movie, which is produced by the ISC to illustrate that once a mode is excited, it starts to travel. it travels into the deep interior of the sun or the star. And what we see is that this is ray tracing, that different oscillation modes, which is one line each, they reach different depth. And if we understand how to read the pattern, we can learn from the difference that the oscillation modes experience in the stellar structure. Each oscillation mode is an individual probe to the stellar structure. One is not telling us a lot, but if we have several, we can learn from the differences and reconstruct in a differential way the stellar structure. At the surface, what they're doing is that those waves, they alternate the temperature field. And the temperature field leads to a luminosity variation, which then we can measure by telescopes like Kepler, TESS, or in future, hopefully soon, Plato, where the group at the IC is heavily involved. It's also alternating the velocity field, because this is a pressure wave going through the outer atmosphere of the star and alternating the velocity field. So we can not only measure the luminosity variations, but also temperature, temperature variations with telescopes like the SONG telescope in Isanya, which is uniquely made to measure these variations at a high cadence. What you see here is a light curve of Aldebaran, for which we follow with the SONG telescopes in several years. The best star ever studied, of course, is the Sun. Tenerife was one of the birthplaces for helioseismology, and the prototype for the golf instrument that is flying on the SOHO satellite shown here is in Isanya in the pyramid. Now, the next generation of that instrument is used on SOHO, which is observing the sun since 1996. And what we see is a time series in photometry and spectroscopy. In asteroseismology, we always shift it to 0, because what this means is that 0 is the equilibrium state of the star, and we see the star oscillating around the equilibrium state. And that already tells us a lot about how the structure of the star is built. Now, we don't really work in the velocity in the time domain, because what happens here is that each data point in this time series has multiple components. It has a component of instrumental noise, of convection, of rotation, spots, and oscillations. So what we do in asteroseismology, as asteroseismologists, is that we convert it into a frequency diagram with the frequency on the x-axis and the power on the y-axis. On what we see is this beautiful power spectrum in blue for photometry and in red for spectroscopy. And we see things in common and things that differ. And with a little experience, we can, or with decades of experience, we can assign different components to this power spectrum, because what happened is that here the power spectrum is separating the contribution to each data point. So we have rotation and spots, we have the granulation component, and most excitingly, the oscillations. Well, of course, opinions might differ, but for us, the oscillations are the most exciting part of a star. And they contain a lot of diagnostic power. So let's call that our little asteroseismic toolbox, because in the power, this axis here of oscillation power, that is proportional to the surface gravity log G of a star and the stellar luminosity. So we already have, simply by obtaining a frequency spectrum, we have already a good proxy on those parameters. If we zoom into this power axis, what we get is a very regular structure. Because we have a very high harmonic oscillation, it's so regular and it has a repetitive pattern. And that's another very nice detail of stellar astrophysics, because the scale, the separation between this repetitive pattern, that is directly proportional to the speed of sound. And if we now measure the effective temperature, we have 3 parameters that describe the density and therefore the radius and the mass. And if we plug that into, if we come into scaling relations with respect to the sun, what we are getting is, from those measurements, the radius, the mass, or G, and the luminosity. And that, once we have those 2 parameters measured, we can do that for every star. And this is done by telescopes like Kepler, TESS, Plato, Roman, or the Chinese Earth 2.0 in the future. So that's what we call the global seismology. Once we have a time series, we can get masses and radii for a large quantity of stars. So this is what we see. This is just from Kepler, that we have about 20,000 red giants as main sequence stars, because every star that has a convective envelope is oscillating with solar-like oscillations. So we consistently can trace the structure from the main sequence up through all variations in the red giant branch. For example, even Aldebaran would oscillate with a 7-day period, which is close to the freefall time. But we can use this over a very large range to measure masses and radii. Remember, this was the small toolbox that we have in our arsenal. The big one comes out, and we can do that really for every star for which we have a time series. There was a recent paper by Han et al., where they reported numaxes and delta nus for more than 100,000 giants. So this, you see, that's what is going into the direction of galactic archaeology and stellar populations. As I mentioned, this was the small toolbox. The big toolbox is brought out once we have high signal-to-noise spectra, and we can assign to each point what geometry on the star we have, on the surface we have. If the oscillation mode is in radial symmetry, or if we have 1 nodal line, 2 nodal lines, 3 nodal lines, and the orientation. And this is where astrophysics happens. Because if we have this information, what we can do is to fit, we can customize stellar models to reproduce this spectrum, and therefore really tune the model to the point. And this is currently the best way of determining masses, radii, and the very ill-constrained parameter, the age of the star, which cannot be measured, only constrained. With red giants, there is something more to it. Because for main sequence stars, as I just showed, what we have are pure pressure modes. Pure pressure modes are only oscillating in the lower density regime in the outer part of the star. As a red giant has often a degenerated core, the density towards the center is getting much higher. So the amplitude of the oscillation mode will be damped as indicated by the color code. Now, you see that in the center of a red giant, because of the density, the amplitude is again very high, even higher than in the outer envelope. But because the density is increasing, the pressure modes are damped out. In here in the core, an oscillation mode could oscillate as a gravity mode, where gravity is a restoring force like a cork on the water. Now, in red giants, this separation is so small that both types can couple and form a standing wave from the surface into the core. And that means that we can probe all the part that is sensed by modes. And because And this detection of mixed modes was one of the first big breakthroughs in red giant seismology with the advent of Kepler. With this, we can measure a couple of things. The main effect they're sensitive on is the density gradient between the surface and the core. And now, as I mentioned before, red giants have several subphases. We have the first phase where we have the degenerated core with the hydrogen shell, and it's really electron degenerated, so a very dense core. At the tip of the red giant branch, that degeneracy is overcome as helium burning is kicking in. The core will expand, the envelope will shrink, and quiescent helium core burning is done in the red lump until the helium is consumed. So you can imagine that a degenerated core and a convective core will have very different densities, and that we can measure by the property of how rapid the core is oscillating. And we get a certain pattern. From the mixed mode pattern, we can determine this frequency. And if we plot it well, this is basically a quantity describing how big the star is. You have the small stars here, you have the bigger stars here. And if you measure this parameter for several hundred stars, you see that they fall into two distinct groups: the rapidly oscillating core stars, and where the core has oscillations of about 50 seconds, 1 minute, or oscillations on the order of 5 to 10 minutes. And this is how we can look into the core and separate between two evolutionary states that from the outside look exactly the same. And there's more to it. Those mixed modes are non-radial modes. And non-radial modes are sensitive to rotation. I don't want to go into details. If you want to then ask me. What we get is a so-called mode splitting. The upper one, here you have, this is a frequency spectrum, a very detailed one, where you have the radial mode, the L2, and you have individual modes. You see they're single peaks. That is for a star without rotation. If we are now looking at a star with rotation, you see that the pattern is changing. We get those little doublets. And those doublets, the separation is sensitive to the rotation rate inside the star. And some of them are dominated by the envelope, and some of them are dominated by the deep interior. And now we can apply what I just said before. We can learn from the differences. And by applying this, we can measure the rotational gradient between the convective envelope and the core, and study angular momentum evolution as a function of the red giant, of the cell evolution. So when I took the date today for my seminar, I did not realize it was May the 4th. But then yesterday I realized on May the 4th with you, I will give a talk about binaries, and I could not resist in including a binary reference to that when transitioning into the chapter on how we are applying this arsenal, those two toolboxes for red giants, for binaries. So first of all, why are binaries interesting from a point of view for astrophysics? Binaries are offering us two virtually identical stars that have been formed under the same initial conditions. They're from the same cloud, same age, same distance, and same metallicity, and in particular important, same initial helium, which is one of the three parameters for any model that we cannot constrain for measurement. It's a three parameter in a model. Now, we have those two parameters, and the main difference is the mass. And the mass is the single most important factor that is governing the speed of stellar evolution. And by using this, by all those parameters that we are having, we either can cancel out or constrain a lot of unknowns. And this is very important. This is very helpful when constructing stellar models. Furthermore, because we have two stars bound to one common barycenter, we can use the laws of Kepler to determine the masses, which is the single most important parameter, better than with any other technique, if inclination is known. And just to show one of my favorite systems, and this was a paper that I wrote here at the IC during my Fundamental server, is a system where we have two red giants. And we know from the mass ratio, we don't know the inclination, but we know from the mass ratio that they have a difference of 1.5%, 1 to 2% mass difference. But all the other parameters, all the differences, we have a difference of 15% in temperature, surface gravity 50%, luminosity 20%, and lithium 17%, 7 times, a factor of 17 times different. They must be at the same age, but why are they so different? And if you look at the time series of autocorrelation functions, you see that the primary is much higher than the secondary. You even see it from that point. We were really curious, or no, curious is the wrong word. We were really frustrated for several years because we couldn't make sense of it, until we realized that this system is in a very particular phase in the stellar evolution. And it has a couple of more features. It's the prototype of binaries with two oscillating components. So we have two red giants of which both are oscillating, which means we can apply the seismic toolbox to both of them if we get enough signal to noise, which is honestly only the case for the primary, but this was good because we could show the evolutionary state, we could constrain the co-rotation and compare it with the spotted light curve, and they agree within the error bars. So a lot of astrophysics we could do there already just from the seismology, but then we realized that this system is located in what we call the first stretch-up. The first stretch-up is an episodic event of mixing at the beginning of the red giant branch. So here you have the main sequence, then the star is ceasing its hydrogen burning, becomes a subgiant, goes into the course degenerating, and then we go up the red giant branch. And in this phase where we have this knee, what happens in the stellar structure is that the convective envelope is eating itself into its maximum penetration. About 80% of the mass of the star are convective. And what happens is that a lot of material is mixed. You have dilution effects, you have mixing effects. And a little later, what happens is that even the nuclear processed material from the main sequence phase will be mixed up. So you have a very particular phase pattern of changes. And we looked at lithium. We also see changes in CNO, but that is left for another paper. And we use the differences in lithium to model the history of rotational mixing inside the star. Now, this is when I learned that if theorists and observers speak about rapid and slow rotation, we mean different things by about 1 to 2 orders of magnitude. But we concluded we could show that this lithium abundance and change in lithium abundance is only compatible if the main sequence star progenitor was rigidly rotating, which is in agreement with other diagnostics. So this binary shows what binaries can be used for to calibrate characteristic models or to improve, especially not only the basic, but the more complex physics of microscopic and macroscopic mixing inside the star. Now, the next step is, I say we have two oscillating components. And the next step is that we want to use the seismic components plus all the spectroscopic and photometric conditions to model, to have a differential Mesa model to constrain the age of the star. And this is done by one of my master students. Right now, this is the first assault. And we hope that his Gaia fellowship interview in 2 weeks is going very well. Now, taking a different step. I mentioned before that the mass can be determined from the binarity. But there was a study a couple of years ago that if you take the dynamical masses of oscillating giants in eclipsing binary systems and compare them with the dynamical masses, they can differ with up to 15%. On the radius, up to 5%. It's not a full, there is reason to believe that this is partly correct, but it's not a fully accepted pattern because as a star is advancing the red giant branch, a lot of effects are taking place, in particular non-adiabatic effects. So what we want to do is to populate this diagram much better. So we have 14 stars in here, and this was 2016. We're nearly 10 years later, and the diagram is still not better populated, which leads us to the question, where are they? So we could take an artistic license from Fermi and say, where are they? Like, where are the aliens? We know from population studies, like the one from the reviews here, that we expect for a 1 solar mass star, or typically for K, G, and F stars, we expect a binary rate between 30 to 60%. If we are having 100,000 oscillating stars and we find 100, well, I'm not so good in math, but I think that's not 50%. So where are they? And that leads us to a little to all the biases that are introduced. For example, well, here's another stellar model. I have to say those James Webb images are getting better and better. This is a diagram from Gaia, from the latest Gaia DA3 data set, where this is, I think, 10 million randomly drawn a representative Hertzsprung-Russell diagram. And you see very nicely the main sequence, and of course, most importantly, the red giant branch and red nut. And what I like about this diagram is that they took the contours and show where the eclipsing binaries are settled. Which means, here's the red lump, the red giant branch is completely unpopulated. Which, well, completely, given that there are 2 million data points in here and we have a few, there is some systematics in here that needs to be understood. And the thing is that because giants are so big, they need orbits of several hundreds to 1,000 days. Otherwise, and with this, it's very difficult to find eclipsing binaries, because what happens if the binary system is growing bigger, the cross section of the two is getting smaller, and we need a more accurate alignment along the line of sight. So we're very close to the edge on orientation of the binary system. Otherwise, we will, in this case, we will not see any eclipses. We can spot them via radial velocities, but with a radial velocity, we don't know the inclination. That is the big advantage of the eclipsing binaries, to have the inclination simply from the fact that we have eclipses. So how to get the eclipse? How to get the inclination? There are several ways. First, we can do it the traditional way of increasing the sample and hoping for the best. But if you remember the latest results of Gaia, that might be a bumpy road. The other option might be that we have astrometric inclinations from astrometry, but until before Gaia, that was only possible for the closest binaries and the widest. One example is Theta 1 Tau, a 16-year binary orbit in the Hyades. That's that's in front of our door. That's about what, 300-400 light years away. That's giant, and that could only be resolved from specular interferometry. So, or the third option, and you already saw that I picked it out, is from heartbeat stars. This is when we have tidal interaction and we get a particular light curve, but it's a non-very detailed measurement. So you know it's about 45 degrees plus minus 20. Okay, that gives me error bars on my mass that you cannot use. But let's walk two of the roads. First, this was the sample until 2021. We had in total 50 binary systems. Now, what was the problem? We searched for signature of binarity in the light curve. But this was, for this you need either an eclipse or a heartbeat event. And you're limited to the time base of the observations. That means you will catch everything that is shorter than the 4 years of Kepler, for example. But to give a giant space to evolve, you actually need to go that way. Now, because of the 4 years are so characteristic, what this data set gave us was a bias towards the smaller red giants on the red giant branch, not the helium core burn. So every calibration we derived from was actually biased towards very steep density gradient. Now, I used the 9th catalog of binary orbits in combination with Gaia DO2 to simply search. Okay, let's turn the strategy. We know we have binaries. Now let's search which one are red giants, and then with TESS, every brighter star has been observed. Let's search if we can find oscillations. And with this, we found about 1,000 candidates in Gaia and started to populate that diagram slightly better. We tripled the sample size. But if you want to take a guess, no eclipse in binary there. So now we started to at least get the bias, remove the bias, but still no eclipsing system. That was pretty annoying. And then about a year ago, the Gaia DO3 came. With Gaia DO3, a lot of new data products were available. Among others, the Kepler, the two-body orbit by Anu, which contains 500,000 of orbits, including those with inclinations. And if I'm slightly sleepy, appearing sleepy, that's because this paper was just submitted today at 3 o'clock in the morning. What we did was a major search, a cross-section between the seismic database and the Gaia database to search for new binaries. And we combined in this study Gaia, then Kepler and TESS, and the Sloan apogee spectroscometer for independent confirmation. The first step we did was to take again the SB9 catalog, because it's a new database. And at all the conferences, people say the validation is left to the community, right? That's the sentence I heard several times at conferences. So we had to build up experience. So we took literally ground truth, because the SB9 is based on ground-based observations with spectroscopy. We simply wanted to check how many stars are in the two-body orbit catalog. And the result was pretty encouraging. About 30% of all stars in that catalog are in the sample. Then also the residuals were pretty encouraging, except that there are some trends, as you can see, with increasing values. Of course, as you approach the baseline of the satellite, they are escalating, but well, that's the way it is. And we found that up to 99% of all systems, as a function of the time, they agree within 10% of the literature value, which was pretty encouraging. And we also built a better understanding for the Ruwer parameter, that this is not the unique decisive measurement, but one way of finding. But there are binaries, but there are several other ways. We searched more than 30,000 known oscillators and cross-checked them with the 500,000 of binaries in the catalog. And we found a binary detection rate of 4%, which, if you think of the 40% we expect, is a factor of 10 difference. However, you have to take into account that red giant binaries, for example, are much longer orbits. And we had to take into account that the Kepler sample is fainter than the sweet spot for Gaia. So there were a couple of biases to take into account. And I will come back. So this is the new Hertzsprung-Russell diagram. Every dot in here is a new binary system. And in total, we found 950 new binary systems. We validated them. We vetted them by using the global seismology, for example, to determine the mass and the radius. And this is the stellar mass versus radius diagram. And we found a little alarming or worrying detail that for stars observed with TESS, there seemed to be some noise. So every star observed with TESS showed solid oscillations above roughly 20 solar radii seems to have an overestimate in the mass. So that's independent of binaries, but in this study, we showed that TESS, or the red and the gray dots, and disagree with the Kepler distribution shown in black. We tested if the radius, we tested if the binaries are plausible and if the orbit is plausible by using an estimate of the rush slope in the plane of the orbital period versus the radius. And except those systems, all the others are in good agreement with what we expect. Even more, you see a little gap here. Let me highlight that. That could be the effect of tides. Meaning, because tides, if you have close interaction, tides are inducing activity, and this activity is suppressing oscillations. So we see this gap here as an indicator that these are actual systems we can believe in. Now, the LACMUS test is ground-based spectroscopy. And we have 900 systems that nobody knew of could be of interest. So we went to the Gaia, to the Apogee database and searched for which of the targets had at least 2 observations. And if the 2 observations agreed disagreed significantly from each other, we could say those are binaries. And with this test, we can confirm out of 181, we can confirm 82%. And that's a very high fraction. This is a very small number compared, so the stars which had observations are a very small number compared to the 900, but the thing is that we require at least 2 observations, which are not yet, but this will grow better with forthcoming data releases of Gaia, of Apogee. For some, we have a lot of radial velocity variations, measurements as shown here. For example, this one is beautiful. And to test the periods, we folded the radial velocities from apogee with the Gaia period. And all of them make perfectly sense. So we see that this is a good validation of the targets that we have. So this is the diagram as we get it. This is the orbital plane, the orbital period on the horizontal and the eccentricity on the vertical axis. And those are the ones that seem to be too short, because the orbit would be smaller than the giant. However, it's reported that due to some artifacts, extremely short periods are reported for actual binaries. So that's why we kept them in. And they could be pointing towards realistic diagrams, to realistic systems. What we notice is that they are all very much locked at the 1034-day baseline, which at the very long periods, they are underestimated. So that's with Gaia 4 and 5, many of them will move that way. So we need to take that into account for systems longer than that. If we take all the effects into account, we can also show that the population, if we take yield corrected values, if we add non-full solutions and correct for the incompleteness factor, we actually get to the 30%, which is another argument that we believe that most of those systems are realistic. Several of them have inclinations, which means from astrometry, which means that for those we can get dynamical masses, and we just submitted a LCO guaranteed time program proposal to the IC to get radial velocities for the brightest targets to actually get the velocity component for both. And finally, we found out of 30,000, we found 2 eclipsing binaries hosting a red giant, and one of them is oscillating. The other one probably is oscillating, but too faint to show its oscillations in TESS. So, well, that's the thing. The final finding, and for me the most fascinating one, is that we can catch stellar and binary evolution, the dialogue of stellar and binary evolution on the fly. We are dealing with tides. So this is an extreme example, and I copied it from a different press release of the IC where oscillations were found in a oscillating giant. But you see the star is deformed because it cannot be approximated as a point source, and you actually have this deformation. This is what is called the equilibrium type. There are 2 different types, but this is the equilibrium type is the simpler one, which is simply a deformation. And dissipation of tidal energy is the transformation of potential or angular momentum into heat and through friction. And by this process, you're driving the evolution of a binary system towards the equilibrium, where the spins are aligned, the rotations are synchronized, and the orbit is circularized. That's a binary system in equilibrium. The thing is, for the equilibrium type, the radius goes in as a function to the power of 8. So it's highly sensitive. And in the red giant phase, a star like the sun can vary its radius from 1 to 200 solar radii. So if you plug that into here, you can imagine that this is a pretty big change. So we would expect, even if we have very wide systems, you would expect differences in the distribution. Let's assume stars are born with a very random uniform distribution in period and eccentricity. You could imagine that this tidal evolution is changing the distributions. And if we used the seismic information, the evolutionary state, to color code systems for which we could determine if we have a hydrogen core, helium core, or hydrogen shell burning phase. And you see, just without even reading, you see that the colors cluster in different regions. In particular one, the teal ones, they are around 1,000 days and centered towards lower eccentricities than the orange ones, which are the hydrogen shell burning. Now, if we plug that, if we take histograms, we see clearly that those stars that have ignited helium at about 200 solar radii tend to be less eccentric than those that have ignited helium much lower, because they are much more massive, at 30 solar radii. And we also don't find them at the big ones at shorter periods, simply because they were so big that they were eating the secondary. For me, this is the first result where we can actually quantify those differences that always were expected and also shown from different, suggested from different studies. But here we now, for the first time, can show that this is real. And now theorists probably are very happy to take this and calibrate the tidal models. With this, I summarize that applying the small and the giant toolbox of asteroseismology to binary stars is a very valid step to learn more about the evolution. And I would like to say that with the numbers, we now have increased the number of binaries by an order of magnitude. And we have a full wealth of information. We are first of all entering the age of ensemble binary seismology, which allows us to not only view the stellar and the binaries evolution separate. No, it allows us to show how the two co-involve. And with that, I yield back and take your questions.
Thank you, Paul. Just in time. So question time now for the audience here at the aula.
Thanks. That was very nice talk. I have two questions. One is, what is the precision you need in radio velocity?
What for?
For confirming the rest.
How
many points like?
Okay, so it probably a few 100 meters a second would be enough if we want to do the binarity, but we need the SP2 solution. So also it's not only RVs, but also higher signal to noise.
And the other question is, in that plot where you talk about rotation.
Yeah.
I didn't understand exactly the curves. Then we have two curves, like half of the points, and then you had the black one. Is that one with rotation?
You mean? You mean with lithium?
Yeah.
Yeah. Okay. Yeah. Really there? Really there? Could be there. Yeah. So yeah, so those are the measurements of the lithium as a function of the effective temperature, which is a evolutionary proxy. What the different models are in different colors are different evolutionary models, assuming different rotation history. One was the rapid rotation, and the other ones were slow rotation, and the black one is the curve of rigid rotation. And in that case, we limit the rotational mixing, and that's how we preserve the lithium to the point as it is observed.
More question.
Please. Motivating also. The binaries that you have identified in the Gaia Center.
Mhm.
Do you have the basic physical parameters on most of them? Or not?
Basic.
The basic physical parameters, radius, masses.
Yep.
You have them.
So the paper is 25 pages of text and 40 of tables where we give all the parameters we have.
Classified as
Yeah.
Have you made any simulations of what fractions we can expect?
No. Okay. Well,
0.1% or 0.2% is extremely low. I know, but for example, by that some Jupiter system is randomly oriented as 0.1% of the sun system is 1%. Here we talk about two large stars that are orbiting each other on orbits that are apparently on the order of a year or less, or a bit more. And in any case, mixing probabilities are on the order of percents.
It's not only, well, okay.
But you have to fold it with the coverage of Gaia, I think, so it's a known eclipse or an unknown eclipse. And maybe with the data release 3, which really will show the full-time series, we will find much more eclipses.
Yeah, with 4. Yeah, what we are also checking is Assassin. So we took the 6 systems that were within 3 degrees to the edge on. We checked them with, what was it, 8 years of Assassin data. We knew the period, and we didn't find any eclipse. So those basically edge on, we didn't find. So and we have turned every stone in the Kepler data, and out of the 20,000 Kepler giants, we find out 20 eclipsing systems, and
should make very easy simulations how what fractions you would get.
Okay.
Or period radius. That's really all you need. Absolute radius in the field.
We should have a coffee about that.
Yeah. Okay.
If not, let's thank Paul again. And just 2 more things. 1, PhD student, go down here, sit down here and write their names. 2,